Section 9.8, complex number system, is about the set of complex numbers. To get there, it takes a while, kind of building our way, working our way, beginning with the set of numbers that it looks like maybe we might need, and then asking ourselves, is that enough numbers? Or do we maybe need more numbers than that, until we finally get to the complex number system, in which hopefully whatever need for numbers that we'll have will be completely satisfied with all that the complex number system has to offer. So, to begin with, we need numbers to count things. Want to know how many of this, how many of that, how many camels we have, or how many crayons we have, or how many, whatever it is, we need to be able to count them. And so just kind of on a real basic level, we need numbers to count things, and numbers that we count things with are numbers like these: 1, 2, 3, 4, 5, and so on. Sometimes these are called the counting numbers. Most textbooks tend to call them the set of natural numbers. Natural in that they don't arise because some sort of algebraic property needs to be satisfied. We just need to count things. So we count them, and we use these natural numbers to do it. At some point, we realize the need for a number to describe how many crayons we have. When we have no crayons at all, that's not a natural number. What we would need is 0. And 0 is a whole number. All of the natural numbers are also whole numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. All those are considered to be whole numbers. 0 is also considered to be a whole number, even though it doesn't technically belong to the set of natural numbers, because we usually don't use the number 0 when we count things. So, it's a whole number. These are great numbers, both these sets of numbers. They both have these properties. We can add any two natural numbers together. We always get a natural number as the answer. We can add any two whole numbers together, even the same whole number twice, 0 plus 0. And we're guaranteed to get a whole number as the answer. Multiplication is kind of a shorthand version of addition, so it also applies for multiplication. We can multiply any two natural numbers together. 19 times 17. We might not know what that is right off the top of our heads, but we know it's going to be a natural number. Both those numbers are whole numbers, so we know it's also going to be a whole number. So we can multiply, we can add all day long with reckless abandon, without fear that our answer will not be a whole number if the numbers we're adding, the numbers we're multiplying, are whole numbers. We say the set of whole numbers and the set of natural numbers are closed under the operation of addition, and they're closed under the operation of multiplication. However, when it comes time to subtract, we have a certain number of objects, and maybe we owe somebody else a certain number of objects, maybe more than we actually own, and so we have to subtract a larger number from a smaller number. We're not guaranteed that we'll get a whole number as the answer. Let's see, what would be an example of such a situation? Well, keeping it as simple as possible, I guess. How about 1 minus 2? Okay, we own 1 camel, but we owe our neighbor 2 camels, and so our net worth in camels would be -1 camels. So that's a problem that we're going to have to work, I guess, over time to resolve. But numbers like -1 and -2 and -3 and -4 can be obtained by taking whole numbers and subtracting one whole number from another. If we subtract a larger from a smaller, then we might get a negative number. So basically what we want to do is toss in all the opposites of all of the natural numbers together with our whole numbers. And if we take all these negatives together with 0 and all the natural numbers, what we get is the set of integers. The set of integers includes all the natural numbers, all the whole numbers, all the opposites of all the natural numbers. And so there are lots and lots of these. And the set of integers adding those negatives is nice because not only can we add, and we need to check this, 40 plus negative 19. Whatever that is, when we add two integers, we're guaranteed the answer is going to be an integer. Even if something like negative 17 plus negative 20, we're guaranteed that's going to be an integer. So we can continue to add integers. Can we multiply? Well, we have rules for multiplying, whether it's a negative times a positive, or a negative times a negative, or even a positive times a positive. Whatever these answers are, they're guaranteed to be integers. We're not going to get, well, an example of a number, we're about to go there, that's not an integer, would be a fraction like 3/4. We're not going to get 3/4 as the answer if we add, multiply, or subtract any two integers together. So, set of integers is closed under the operation of addition, under the operation of multiplication, and under the operation of subtraction. But when it comes to division, we may have a problem. If we take 3 and try to divide it by 4, well, we get an answer, but that answer is not an integer. Okay. 3 divided by 4. It can be written, well, it actually was obtained by dividing an integer by an integer, so it can be written as the ratio of an integer to another integer. So we call it the rational numbers. Set of rational numbers includes these fractions like 3/4 and like 4/3, proper fractions, improper fractions, positive fractions, negative fractions. But it also includes numbers like -3 and 0 and 5. All these numbers that we have up here so far belong to the set of rational numbers. How do I know that the number 5 is a rational number? Because I can take the number 5 and write it as an integer divided by an integer. That's not the nicest way. How about this? 5 over 1. If I could take a number and write it as an integer divided by a non-zero integer, we don't want to divide by 0, then it belongs to the set of rational numbers. And if it belongs to the set of rational numbers, either it can be written as a terminating decimal, like that. 0.75 just stops. Doesn't go on and on and on. You can put a whole bunch of zeros after it if you want to. But you don't have to. 0.75 says it all, about 3/4. Or it's rational if it can be written as a repeating decimal, like 1.333 ... where there's a fixed sequence. In this case, it's just a sequence of one digit, 3, that repeats over and over and over again, and that's what the decimal expansion consists of. That's a rational number. All right, let's stop and ask ourselves, is this enough numbers to do all that we could possibly need to do? Not quite enough numbers. And a good example, I think, to show that this is not quite enough numbers is a square that's 1 foot this way and 1 foot that way, or I guess a little bit more than an inch up on the big screen there. Whoa. Try to draw the diagonal of this square. How long is the diagonal? If I could just draw it. You get the idea there. Straight line from one corner to the opposite corner. How long is that? It's got to be longer than 1, right? There's no way that's just 1. But I think it's not as long as 2. If I walk from here over to there and then up to there, that's farther than if I go straight across. So some number between 1 and 2. Well, there are a lot of fractions and decimals that are between 1 and 2, but what's this? Yes.
Is it like 1 times square root of 2?
It's very much like that. We can get that using how? How can we show that's what it's equal to? 1 times the square root of 2, or just the square root of 2 if we simplify that. If A is 1, and B is 1, and C is not sure yet, and we have a right angle here, How do we figure it out? Solve, find the longest side of this right triangle. What's the theorem? How's it go?
A squared plus B squared plus C squared.
That's the one. The Pythagorean theorem. Or a student was in graduate school with me, who actually her home was in Athens, Greece, called it the Pythagorean theorem. So, okay, that's how they say Pythagorean. Near where Pythagoras, I guess, was from. Nonetheless, though, Pythagorean theorem, 1 squared plus 1 squared equals c squared. 1 squared is 1, 1 squared is 1. 2 equals c squared. What number can you square and get 2? Not a real nice number, not a rational number. You can square the square root of 2. And when you square the square root of 2, you get 2. So it is the square root of 2. Now I can't, well, I could, but don't want to take the time to do it, prove that the square root of 2 cannot be written as an integer divided by an integer. It turns out that it can't. Pick an integer, any integer divided by any other integer. It's impossible to get the square root of 2 exactly by doing that. You get real close as you want to get to it with integers, but you can't get to it exactly. So we need more numbers. And at this point, I think I want to depart from this practice of just going bigger and bigger like this. And I want to put another something like this. It's a little bit deceptive the way I'm doing it, because if you look at the real number line, on the real number line it consists of two different types of numbers. Pick any number on the real number line, it's either going to be rational or it's going to be irrational. Every number on the real number line can be classified as one of those two types of numbers. And it turns out, although we spend most of our lives dealing with rational numbers, for those that study such things, there are way more irrational numbers than there are rational numbers. So it might be a little deceptive that I make this little rectangle to hold all the irrational numbers smaller. But we just don't think of a lot of examples of them. I mean, in this class, we look at the square root of 2 and the square root of 3. We look at the cube root of 19 and the fifth root of 7. If it's the square root of something that's not a perfect square, it's irrational. If it's the cube root of something that's not a perfect cube, it's irrational. If it's the fifth root of something that's not a perfect fifth power, it's irrational. But then there's also a number like pi. Draw a circle, measure how far around that circle is, the circumference, and divide that by how far across you go, the diameter, and you get pi. That's also an irrational number. You can't take an integer, divide it by an integer, and get pi as the answer. So we got irrational numbers. If we take the rational numbers and the, oh, didn't mean to erase all that, the rational numbers and the irrational numbers and join them together, we get the set of real numbers. How to make the diagram look like it's take all the rational numbers and the irrational numbers, put them all together, you get the set of real numbers. Well, that's what you get. Okay, whew, that took some work. Is this enough numbers?
Yep.
It would seem to be so, right? Because we can solve triangles if they have real side lengths. Whether they're rational or irrational, we can do that. And there are a lot of other great things we can do with real numbers. However, we can write down some pretty simple looking polynomial equations with real coefficients. What's the coefficient of x squared? It's invisible, but what is it nonetheless? 1. Plus another 1, pretty simple, equals 0, pretty simple. So a polynomial equation, a quadratic equation, of which we solved some, but there's no real number that satisfies this. If you take a real number, because look, what, if you subtract 1 from both sides, x squared equals -1, If you take a positive real number and square it, positive times its own positive self is not negative 1. If you take a negative real number and square it, a negative real number times its own negative self is going to be positive. Not negative 1. 0 times 0 is certainly not negative 1. There's no real number that makes this true. So if that's all the numbers we had to work with, we just have to shrug our shoulders and say, no solutions. It's because there's not one on the real number line. That turned out not to be satisfying to mathematicians a few centuries ago. So, made up a new number. The square root of negative 1. The square root of negative 1. If you square it, what ought to happen? The exponent and the radical sign simultaneously vanish, leaving us with what? Negative 1. Now we've already just noticed that the square root of negative 1 is not on the real number line. You draw the real number line, there's no place to go and put a dot, point to it, and say that's the square root of negative 1. It's not on there. So, we give it a name, we call it the imaginary unit. The imaginary unit. Oh, and it's got a symbol associated with it. What symbol do we use for the imaginary unit? It's little I. There it is. I equals the square root of negative 1. Together with the number 1 itself, they will be building blocks for the set of complex numbers. Let's first look at one important property. If we take I and square it, I itself is imaginary. The imaginary unit better be imaginary. But if we take it and square it, we get negative 1, which is real. So, although I itself is an imaginary number, it has a connection to the set of real numbers because its square is a real number. We'll look at some other powers, hopefully, before we go today. But in particular, I squared is negative 1. Well, there's no place in this great big box that I've drawn here to put I. Hopefully I've captured it all. So let me add on to the box. Maybe down here. So we've got the real numbers. Down here we're going to put the imaginary numbers. Beginning with I. But what do you suppose would happen if we take a number and multiply by, take a real number and multiply it by I, like 2 times I? Would that be real or imaginary, you think?
Still imaginary.
It's still going to be imaginary. It turns out that a real number, a non-zero real number times an imaginary number is an imaginary number. If we take a real number like 3 and add it to I, that also belongs to the set of imaginary numbers. 3 plus I is an imaginary number. Or we could say 3 plus 2I. That's imaginary. And the real numbers don't have to be nice. They could be irrational. We could say the square root of 2 plus pi I. We won't, don't worry. But we could. And that would be an imaginary number. Square root of 2 plus pi I. So each of these numbers belongs to the set of imaginary numbers, but there's a bigger set that includes, where do I write this? A bigger set that includes all of these, and I guess I'm just going to have to do it like this. I'm going to have to scoot the square root of 2 plus pi I down just a little bit, maybe put it over here, bring it back. It's the set of complex numbers. What's a good vivid color here? Red, I suppose. Complex numbers includes both of these. All the real numbers, all the imaginary numbers put together, we get the set of complex numbers. And put that in the form of a definition. The set of complex numbers is, and I'm going to write it using set builder notation. It is a set, so it's an appropriate type of notation to use. The set of numbers that can be written in the form a plus b times I. We know what I is. It's the square root of negative 1. A and b are real numbers. When we put it in the form a plus bi, we say the number is in standard form. It's a standard form of a complex number. That way we can look at it and see what its components are. The a is called the real part. It's a real number, doesn't have an I with it, so we call it the real part. The b is called the imaginary part. We've got a real part and an imaginary part. Notice that b is multiplied by the I, but the I itself is not part of the imaginary part. It's next to the b is next to the I, so we call b. B, like, answer the question, how many I? How imaginary is this number? How many I? So b is the imaginary part. When we add complex numbers, when we subtract complex numbers, when we multiply them, divide them in a little bit, we want to make sure that the final answer is in standard form. All right. The main reason we need these complex numbers is that when we solve quadratic equations in the next chapter, 10.1 and 10.2, a significant portion of the time we're going to get the square root of something negative. And we just want to have the best form to express the square root of something negative. That's really why we need these. I mean, there's a whole rich study of complex numbers, complex number theory. But for our purposes, we're going to keep it simple and just say, well, what if we run into the square root of negative 64? Rather than just saying, not a real number, walk away from it. What's the nicest way to write this number? Well, if a is positive, so that negative a is negative, the square root of a is defined to be I times the square root of negative a is defined to be I times the square root of a. Now this sort of mimics the product rule, because if we have the square root of negative a, I personally think it makes sense to think of this as the square root of negative 1 times the square root of a. I have to be careful. If a is negative, this doesn't quite work out, even though the product rule would suggest that it would. But if a is positive, we get by with this. The square root of negative 1 is I. So this is I times the square root of a. Now, the way I write the I, it doesn't quite look like this. But if one was maybe not too careful, a good way to remember this, I think, although I don't know how pedagogically sound this is, if we have the square root of a negative number, grab the negative sign, bring it out in front of the radical, and put a dot on top. Okay, that's silly. But it works every time. If it didn't work every time, I wouldn't mention it. I times the square root of 64. Once you get the negative dealt with, you can deal with the square root of 64. What's the square root of 64?
8.
It's 8. So this is I times 8. Or it's 8 times I. I like 8 times I better. Does it make sense that 8i should be regarded as the square root of negative 64? If we take 8 times I and square it, would that give us negative 64 back? Well, it would give us 64i squared, right? Square the 8, square the I. But what's I squared?
Negative 1.
It is negative 1. So that's 64 times negative 1, which is, there you go, negative 64. So it kind of does make sense to say 8i, even though it's not on the real number line. It functions as the square root for negative 64. Square root of negative 24, not quite as nice because negative 24 itself is not a perfect square. We can still do this though. This is I times the square root of 24, and then we simplify the square root of 24 as much as we possibly can. I times the square root of 4. We just think, what's the largest perfect square factor of 24? That's 4. And then the other factor is 6. And then we can say that's I times 2 times the square root of 6. And various ways to write this. I don't think Alex would like it if you put the I all the way in front of the 2. I think Alex would be okay with it. Let me know if they're not. If you say 2i times the square root of 6, because it's so often done, technically, I'm going to put a box around that and say that's done.
I think he likes that, yeah.
It's okay with that? Technically, it's 2 times the square root of 6 times I. So you look at it and say, what's the imaginary part of this number? Well, it's 2 times the square root of 6. That's the coefficient of the I. So it's maybe not best form to split it up and put the I in the middle. However, there's risk in writing the expression like that, because if one is not careful, the I could slip up underneath that radical sign, and the square root of 6i is not the same thing as the square root of 6 times I. So just as a precautionary measure, I like to put the I in front of the radical. If you put it after the radical, so long as there's enough daylight in between where I know the I is not underneath the radical sign, that's fine. Square root of negative 50 is similar. I times the square root of 50. What's the largest perfect square factor of 50? 25. So we can write that the square root of 25 times the square root of 2. We can write that I times 5 times the square root of 2, or 5i times the square root of 2. Not too bad. That's basically what we need for these complex numbers. Now, there's a little bit more we're going to do in this section just for the sake of, okay, we've got this new set of numbers, ought to know how to add them, ought to know how to subtract, how to multiply, how to divide. But beyond this section, all we'll need to know about complex numbers is basically what we see in this example. That's not to say it won't be on the Chapter 9 test, adding, subtracting, multiplying, dividing. But you don't see much of this adding, subtracting, multiplying, dividing that we're about to do, say, in a college algebra course. There are some official rules for how to add and how to subtract complex numbers. And we should at least acknowledge those rules. When we boil this down, I'm going to treat addition and subtraction of complex numbers in very much the same way that I treat addition and subtraction of polynomials. I'm going to treat it like combining like terms. Combining not x terms and constant terms, but combining I terms and real terms. But let's look at the rules nonetheless. If we add a couple of complex numbers, a plus bi with c plus di, we will get a complex number as the answer. Set of complex numbers is closed under addition. That answer will have a real part and an imaginary part. And if we can figure out how to come up with the real part, how to come up with the imaginary part, then we know how to do this. The real part, oops, back to blue. The real part of the sum, are you ready for this? Is the sum of the real parts. Say that again. Although I think it was clear the first time. The real part of the sum, that is, this is the sum, and we're looking at the a plus c there, the real part. It's the sum of the real parts. We just take the a and add it to the c, and we get whatever a plus c is. The imaginary part of the sum, b plus d, is the sum of the imaginary parts. Take the b, take the d, add them together, get whatever b plus d is. Subtraction is similar. The imaginary part, the real part of the difference is equal to the difference of the real parts, a minus c, and the imaginary part of the difference, where's the red? The imaginary part of the difference is equal to the difference of the imaginary parts. We'll do the first problem both ways, and then after that, I'm just going to say, okay, let's clear the parentheses, let's combine the real terms, combine the I terms, keep it as simple as possible. Example 2. So example 2a, if we want to respect that rule up there, we're going to get a real part, and we're going to get an imaginary part times that I. The real part of the first one is 3. The real part of the second one is 4. What's 3 plus 4? 7. Okay, so the real part of the sum is 7. We add the imaginary parts. The imaginary part of the first one is 2. The imaginary part of the second one, uh-oh, careful with this. What's the imaginary part of the second one?
Negative 5.
Negative 5. So, 2 plus negative 5 is what? Negative 3. So 7 plus negative 3i. And when Alex, or when whatever on a test, the problem says write the final answer in the form a plus bi. A minus bi is okay. So the final answer could easily be written in the form 7 minus 3i, and everybody would be good with that. Now, how would we do this problem if we're not thinking about rules for adding? We look at it and we see a couple of expressions, and we realize the parentheses, other than to set it apart and say, okay, here's one complex number, here's another complex number, we're going to add them. As far as the individual terms, the 3, the 2i, the 4, the negative 5i, parentheses don't have a lot of effect on that. So there's not a number multiplied by the parentheses, there's not a negative sign in front of parentheses, so we can lose the parentheses and be okay. 3 plus 2i plus 4 minus 5i, think of it as 4 separate terms rather than 2 complex numbers, each with 2 terms. And just combine like terms. Combine the 3 and the 4. Get 7. Combine the 2i and the negative 5i. Get negative 3i. This problem is missed on tests way too often. It's not a difficult problem. Just deal with the parentheses and combine like terms. B part is a little trickier in dealing with the parentheses. What do we have to do if we're dealing with the parentheses in the B part?
Change signs.
Right. Minus 11 plus 2i. 11 minus 2i goes from plus minus to minus plus. So minus 11i plus 2i. But then, once the parentheses are gone, combine like terms. Real terms, I terms. 7 and negative 11 combine. They give us negative 4. Negative 6i and 2i combine. And they give us the minus 4i. So subtraction, not too bad. There's a nice visual. Let me see if I can find this visual. Where is it? It's probably here. Let me see if I can find the nice visual for this. Because there's one way to visualize. I know that you can't visualize an imaginary number on the real number line because it's not real. But it has 2 components, a real part and an imaginary part. And if you consider those 2 components, you could visualize it. Where does it say operations with complex numbers? There it is. You could let the real part be where it is along the x-axis, and let the imaginary part be where the number is on the y-axis, basically. And this is done. Let the real axis, the x-axis represent the real part, and the y-axis represent the imaginary part. And if you have a number like negative 2 plus 3i, you can say 2 to the left and 3 up, and just put a dot there and say, this is a representation for negative 2 plus 3i, that complex number. And if you have 7 plus 2i, you can go 7 to the right and 2 up and say, well, there's 7 plus 2i. It's not on the real number line, it's It's off the real number line, so it's an imaginary number. And if you add them, the -2 and the 7 add together to equal 5. And the 3 and the 2, well, in this case, also add together to equal 5. And notice the visual you get. We don't talk about vectors in this class, and we're not going to start now. But if you just kind of draw a line straight from the origin to -2 plus 3i, and a line straight from the origin to 7 plus 2i, and then you want to add those two complex numbers together, you can visualize that with the parallelogram. Yes? Parallelogram. You just take the sides of that and kind of move them parallel, and you get, let's see, actually, the visual a little bit better there. You take the 2 plus 3i, is that the one that's moving there? Yeah, there you go. And you move it like that. You take the 7 plus 2i and you move it like that, parallel to that, and you get the 5 plus 5i. And you can change these around if you've got a different problem. If that's something like positive 2 plus 3i, and this is 7 plus 2i, then you get 9 plus 5i up there. You can draw that big long diagonal of the parallelogram, and that represents this complex number addition. So if we can't visualize imaginary numbers on the real number line, we can certainly visualize them in this XY plane. All right, time to multiply. Multiplication. 2 plus 3i times 5i. How should we do this? Distribute. It's a binomial times a monomial. This is distributive property. The 2 gets multiplied by 5i. The 3i gets multiplied by 5i. We get 10i. We get 15i squared, which is -1. So 10i plus 15 times -1, or 10i, I want to say minus 15? I guess I could say minus a -15, and that would, I mean, I could say plus a -15. I wouldn't want to say minus a -15. You can write it like this. Alex might not like this, though. Why might Alex not like 10i minus 15?
I have no idea.
Well, Alex is going to say, put it in the form a plus bi. And this technically is in the form bi.
So -15 plus 10i is the answer?
Right. Just flip them around and write -15 plus 10i, and then it should be okay with it. If it gives you any feedback, it should say, this is equivalent to the correct answer, but it's not quite in the right form. And hopefully and they'll say a plus bi is what we're going for here.
It won't count you wrong. It'll just ask you to write it differently.
Oh, that's nice.
Sometimes it counts you wrong. Sometimes.
Sometimes.
Yeah.
Depending on its mood, I'm sure.
Mm-hmm.
So this was not so bad. B part, 3 minus 8i times 4 plus 2i. How shall we do this? FOIL. It's a couple of binomials. FOIL method should work nicely. Nice streamlined process for the distributive property. 3 times 4 is 12. 3 times 2i equals 6i. -8i times 4 is -32i. And -8i times 2i is -16i squared. Good first step, but we want to write our final answer in the form a plus bi. So obviously more to be done. What can we do next? I think the 12 just comes right down. Combine the I terms. 6i, -32i, or 6i minus 32i is how many I? I want to say 26. Is that it? Minus 26i. So we combine the I terms, get minus 26i. And then minus 16 times I squared would be minus 16 times -1. Oh, we could probably do this in one more step. Or let's take 2, though. 12 minus 26i plus 16. And then finish it up by doing what?
Combine like terms.
Combine like terms. 12 and 16. 12 plus 16 equals 28. So 28 minus 26i.
That's one of those problems. That's one of the square the first one, right?
The C part?
Yeah.
C part is special. There's something really special about the C part. A plus BI, A minus BI. We run into expressions that look like this before with the radicals. Remember when we multiplied 4 plus the square root of 3 by 4 minus the square root of 3? Remember doing that? We had radicals, but we multiplied these together and the radical terms canceled. So even though both numbers were irrational, we got something that was rational. Yes?
So if you have that,
Uh-huh.
it's like anything plus 3 plus 4, 3 minus 1. Can you just go ahead and times 3 times 3, and then like negative 4i, and just skip the other step?
Absolutely. Absolutely. We definitely want to skip this step. We could FOIL this, right? We could say 9 minus 12i plus 12i minus 16i squared. But in this case, if we notice it, you know, the minus 12i and the plus 12i are going to cancel. So we don't have to write that down. We just say square the 3, square the 4i, and a minus in the middle. I still want to think of this as the difference of two squares. There is a formula which is potentially confusing, so I don't make a big deal out of it. I'm just going to kind of direct your attention to it. We're actually going to end up with 3 squared plus 4 squared. We're going to end up with a whole number. But it's going to be 3 squared plus 4 squared. But I've been working so hard, and you've been doing such a good job realizing that the difference of two squares, when you have a plus b times a minus b, you get something squared minus something else squared. I don't want to rock that boat and say, okay, sometimes it's a plus. You know, I'm not going to go there. I'm just going to say it's a minus. And then if that I squared down at the bottom of the page has us do something with that minus, then so be it. 9 minus 16i squared. I terms are gone. I squared is negative 1. It makes it 9 plus 16, which is 25. Yay, a real number. So a plus bi times a minus bi. Now, some fun facts about multiplying complex numbers that you really don't have to know, but they're I think, didn't mean to open a new window there. I think they're sufficiently interesting to mention. As soon as that window opens and I can close it, turn that off. That's the one I want to close. There we go. Show the product. It's just not recognizing this. Fine. Now, these are not particularly nice looking numbers. I'm not going to ask you to multiply 1.64 plus 1.15i by negative 2 plus 3.46i. Even with the calculator, I wouldn't ask you to multiply that out. But it's kind of interesting what goes on when you multiply these complex numbers together. And we're just going to have to trust GeoGebra on this, that it's going to do the computations correctly, because I want to go through the details. But suppose we have a complex number like 1.64 plus 1.15i. And we multiply it by this one up here, negative 2 plus 3.46i. Two things about it which are interesting to me. How far it is from the origin up to that point. And the way I've got this designed, it's exactly 2 units from the origin up to that point. Okay. And the angle. We don't talk about angles in this class. This is not trigonometry. But we can have kind of a rough idea of what we mean by angles. We've got a 45-degree angle and a 90-degree angle. So hopefully we can kind of visualize what 35 degrees is from the x-axis up to this blue little line here, 35 degrees. Let's look at the red one. Negative 2 plus 3.46i, it's 4 units from the origin up to that point. And what's the angle? from the x-axis all the way over here is 120 degrees. 120 degree angle. Now we take those two numbers and we multiply them together, and it's ugly. It is way uglier than 3 minus 8i plus times 4 plus 2i. I mean, look at that problem and just imagine if they're decimals that we have to deal with. And that's how ugly it is. But the calculator does it, or GeoGebra does it, and gets negative 7.25 plus 3.38i. Where do we put that number? Well, we graph it. Go negative 7.25 to the left, or 7.25 to the left, and then 3.38 up, and there it is. But how could we come up with that using the 2 and the 4, and using the 35 degrees and the 120 degrees? Well, if we've got the 2 and the 4, 2 times 4 is 8. That complex number, if we put it right there, is 8 units away from the origin. Some surprising geometry. I don't know that we'd think that just by multiplying an ugly looking number like this by an ugly looking number like that if you take the length of it, 2, and multiply by the length of that, 4, you get the length of that, which is 8. That's surprising to me. But it happens like that. And what about the angles? If we take this number, 1.64 plus 1.15i, which is 35 degrees away from the x-axis, and the 120 degree angle, and we multiply them together, the angle for the purple one is 155. How do you suppose it got that 155? What do you think? Added them. 35 degrees plus 120 degrees. 155. None of that's going to be on the test. Don't sweat that. I just think it's interesting to get the visual. And we can change these. We can make them like shorter, like that. And can change the angles a little bit, like that. But we multiply this one, and it's 70 degrees. We multiply this one, that's 120 degrees. That is length 2, that's length 2. We multiply them together, and we get something that has length 4 and is 190 degrees away from the x-axis. And the computations are ugly, ugly. Multiply that by that using the FOIL method, and then combine like terms and everything, but there it is. 3.94 to the left, 0.69 down. It's pretty amazing, I think. All right, back to business. A plus BI and A minus BI are called complex conjugates. You multiply those together, they're both imaginary numbers unless B is 0. But when you multiply them together, you always get something real. Oh, and I think that's what got my attention. What if I try to multiply two complex conjugates here? Suppose I make the blue one. I just leave the blue one where it is and take the red one. Where can the red one go? Down here somewhere. I think the red angle I want to be 290 degrees. And the blue angle to be 70 degrees, so 290 all the way over there. But notice these two numbers, 0.68 plus 1.88i, 0.68 minus 1.88i, those are complex conjugates of each other. They have the same real part, 0.688. They have opposite imaginary parts, 1.88 minus 1.88. You multiply them together, and you get 4. You get 4. The number's right there on the x-axis, and when it's on the x-axis, that's the real axis in our case here, it's real. So, and it's also the length of this one, 2, times the length of that one, 2. So when you multiply two complex conjugates together, you always get a real number as the answer. That turns out to be important for us when it comes time to divide. Oh, when it comes time to divide. Youch. I think addition, subtraction, and multiplication are pretty clear, at least what to try. If we're not sure what's going to work, it's pretty clear. If we're adding or subtracting, we should clear the parentheses and combine like terms. Treat the I terms like X terms, and everything kind of works out. If we're multiplying, If we multiply something with an I by something else with an I, maybe we'll get an I squared. But as long as we know what I squared is, we can deal with that. Dividing, I don't think it's obvious what to do. In fact, we can't really do the same thing we would do if we had x's. Suppose we had 5 minus 10x over 3 plus 4x, and the problem said, write it in simplest form. We'd stare at it. Maybe think polynomial division, but hopefully think better about that, because that would be ugly. I think we'd stare at it for a while and eventually realize it is in simplest form. We could factor 5 out of the numerator, but that doesn't help us reduce it. There's not a 3 plus 4x up there. That's in simplest form. So there's no natural thing to do if we had x's. It's got to be something a little bit contrived if we want to simplify this with the i's. Well, bottom line is we got to get the denominator to be a real number. And like we've done so many times in the past, we're going to multiply by a fancy form of the number 1 with a view toward getting a real number in the denominator. What can we multiply that denominator by so we'll get something real? 3 minus 4i. That'll do it. 3 minus 4i. The complex conjugate of the denominator. It'll get the I terms to cancel, and we'll have 25 down there. But we also have got to multiply the numerator by 3 minus 4i, and that's the tedious part because it involves some foiling. Whoa. There we go. Yes. Always a winner. There. 5 minus 10i times 3 minus 4i equals 15 minus 20i minus 30i plus 40i squared. Denominator, feel free to call that 25 whenever you want to. I suppose I should begin by calling it 3 squared minus 4i, quantity squared. In the numerator, we have 15 minus 50i plus 40 times negative 1. In the denominator, it's 9 minus 16i squared. In the numerator, it's 15 minus 50i minus 40. In the denominator, it's 9 minus 16 times negative 1. What is 15 minus 40? Let's go negative 25, and then minus 50i, and then I guess we can go ahead and call the denominator 25. Feel good about calling it 25 now. 9 plus 16 is clearly going to be 25. Now this, are you looking at that and thinking we can probably reduce this a little bit? Is that the impression you get? Enough similarities between the denominator and the numerator? And it turns out we can. Let's suppose, though, that we couldn't. Suppose instead of a 25 in the denominator, it's maybe a 13, with nothing in common at all with the factors in the numerator, terms in the numerator. We'd still want to break this apart and write it as two separate fractions, just like this. Negative 25 over 25 minus 50i over 25. And we break it apart and write it like that, so we've got the real term and the imaginary term, so we can see the real part, even if it's a fraction, happily not a fraction in this case, but even if it's a fraction, the real part and the imaginary part. Good news in this case is it's negative 1 minus 2i, so no fractions come into play, but we want to allow for that possibility. Suppose I say 91 divided by 7 is 13. And you're not so sure of that. And I need to prove it to you. How could I check my answer and prove that 91 divided by 7 actually does equal 13 without, of course, using long division? What would be the quickest way to show that? is multiply 13 by 7 and get 91. Well, suppose I say 5 minus 10i divided by 3 plus 4i is negative 1 minus 2i. How could we check the answer? Would it make sense to multiply negative 1 minus 2i by 3 plus 4i? Would you expect to get 5 minus 10i if we did that? Well, it's not that I think we made a mistake, but just want to confirm it. Negative 1 minus 2i times 3 plus 4i. That's negative 3 minus 4i minus 6i minus 8i squared. That's negative 3 minus 10i minus 8 times negative 1. Do you believe that's equal to 5 minus 10i? Negative 3 plus 8 is 5 minus 10i. Yeah, that does equal 5 minus 10i. So it checks out nicely. There's actually one more topic that we have to talk about, and as I consider this final topic, I realize this has been a worksheet-free day, so I need to find some way to track the fact that everybody who's here is here. Oh, here's what we can do. This is the 23rd.
Yes.
4, 23. 1, 4. So I would please start over here. Line that and pass it along, and I'll have a record of your attendance. Powers of I. This is not in the notes, but it's likely something that Alex is going to ask you about. Powers of I. We know the first power of I. Take anything, raise it to the first power, you get that thing. I to the first power equals I. Take I and square it. We've done this one. What do we say I squared is? It's negative 1. What we have not yet done is I cubed. What if we're multiplying 3 I terms together? I times I times I. And we have to deal with an I cubed.
Is that negative 1 square root negative 1?
Is that one?
It would be negative 1 times the square root of 1. It would be negative 1 times I, really, but let's see why. Would it make sense to say I cubed is I squared times I? Properties of exponents. 2 plus 1 is 3. And I squared is negative 1. So it's negative 1 times I. So in terms of I, it's simply, well, negative I. We're stuck with that I since it's an odd power. We're going to be stuck with that I, but it's negative I. More powers of I. I to the 4th power. Various ways we could do this. We could say 3 plus 1, but I'd rather say 2 plus 2. Because I squared is negative 1. And the other I squared is negative 1. And negative 1 times negative 1. There we go. So we do get to 1. We do this enough times, and we get to 1. Well, if we're taking a number and raising it to whole number powers, and eventually we get 1, the next power ought to do what? It ought to bring us right back where we started. It's I, yeah. So I to the 4th times I to the 1st power is 1 times I, which is I. How about I to the 6th power? I to the 4th times I squared, 1 times negative 1. We get negative 1. I to the 7th power. I to the 4th times I cubed. 1 times negative I is negative I. I would say just one more, but maybe there'll be 2 or 3 more. I to the 8th. I to the 4th times I to the 4th is 1 times 1. And that's 1. So say it with me, or don't. It's okay. I, negative 1, negative I, 1. I, negative 1, negative I, 1. You suppose the next one's going to be I? It turns out to be I, negative 1, negative I1, I, negative 1, negative I1. This pattern is going to continue. What's the next power of I after I to the 8th? That equals 1.
I don't know.
I bet you can figure it out. I to the, it'd be around in here somewhere. I, negative 1, negative I1. Are you thinking about 12? Who was thinking 12? Was anybody thinking 12?
Sure.
Yes. What's the next one after 12? I, negative 1, negative I1. Down here somewhere? Are you thinking 16-ish?
Yeah.
Yes. What do you suppose I to the 20th power is?
1.
You think that's 1? What do you suppose I to the 60th power is?
Still 1. No, I'm just kidding. I.
Just want to establish the fact that if you take I and you raise it to any power that's divisible by 4, you get 1. Because if you know that, then you can take I and raise it to the 1003. Right? Yes, right. Is 1003 divisible by 4?
Yep.
It's not. Is 1000 divisible by 4? It is. So you could write this as I to the power of 1000 times I cubed. Do we yet believe that I to the 1000 ought to equal 1? Because 1000 is divisible by 4? I mean, if that's a problem, we could say I to the 4th power to the 250th power. Power rule, 4 times 250, right? That's 1,000. Well, what's I to the 4th power? We did that one. I to the 4th power is 1. Okay, so that's 1 to the 250th power times negative I. What's 1 to the 250th power? It's 1, yes? So that's 1 times negative I. So that's negative I. Right. There's time for one more. I to the 25th power. Is 25 a multiple of 4?
No.
No, but it's a little more than what multiple of 4? $24 or 22? Which one is a multiple of 4?
24.
24. So I to the 25th equals I to the 24th times I to the 1st power.
Mm-hmm.
What's I to the 24th?
1.
It's 1. So it's 1 times I,
So it's times I.
which is I. Yeah. Okay. Alex is likely to ask you that. So
Yeah, it does.
I want you to be prepared when it does. Have a wonderful rest of the day.